Now, first of all, why do we want to detect edges? Like if I look at some random image, let's take this one here. Then we'll look into why we're interested in the edges and how we can get them. But before we do that, since we have a new student here today, and I just want to get to know you a little bit better. Last class I asked everybody to introduce themselves, so I'll ask you to do the same thing. And what did I ask you to do? Name, university background, first year master's, third year bachelor at whichever university, your programming language experiences, your robotics projects that you may have done, your computer vision, robot vision projects that you've done or are working on, your hobbies, and the last book that you read.
Hi everyone, I'm Zach. I'm actually former roommate of Raf. I'm from Taiwan Tech, as in Minnesota as well. Programming language, I'm very, I would say proficient in R and Python. Dabbled around SQL as well for databases. Robotics, computer vision background. I don't have a published paper, but we've done projects like object detection, face recognition, emotion recognition in the previous semester. Oh, we also did violence detection, meaning which images contain levels of violence. So on that level, just detection. Hobbies, most of the time I'm a Latin dancer. That's what I do for fun and go to the gym. Last book that I read, Cambodian history.
Cambodian history, yeah.
I like to travel.
Interesting.
Yeah.
Yeah, good, thank you.
Yeah.
And what kind of Latin dance?
Salsa, bachata, kizomba. Recently I tried hula dancing. Hula dancing.
Hula dance.
Yeah.
He's really good. Yeah, okay, good. Then let's get back, thanks for the introduction, Zach. And let's get back to an image like this. Or let me ask you first, for the project that you did, emotion and everything, that was all based on deep learning?
Deep learning, OpenCV,
yeah,
all those.
Okay, good. So we're going to go with the sort of old school version of computer vision. The main reason for that is because it actually allows us to focus in on what kind of features we actually need and what we're going to do with those features. That's kind of all mixed up and mashed together in a neural network. If you have enough training data and you're not so concerned about overfitting, then the deep learning approaches nowadays are more powerful. They can do, in some sense, more things, but there are some applications where computer vision systems actually run very well and the deep learning approaches don't work so well. So one example of that would be at Boeing, and You may have heard my class from last week where I talked about the fact that indeed our vision systems are far inferior to the kind of face recognition that a 3-year-old kid could do. It's a very, very tough problem, the general vision problem. In the 1990s, that was called the problem of pixels to predicates, being able to understand objects and relationships from an image. That is still, we've made great progress using deep learning in some aspects of that, but that's still a very, very hard problem to solve in general. However, for certain applications, in particular, when you can control the environment, the approaches that we designed and the algorithms that we have are actually extremely powerful and work particularly well. One example is this system that they had set up at Boeing. Boeing Seattle builds the 747, the big airplanes, right? And there they had a machine vision system that they would bring in the part of the fuselage. So that's a very big thing. That's like as big as the wall there. A section of the fuselage. Then they had a vision system that would take a picture and then tell you that rivet hole 2597 is not in the right place. It's 1 millimeter to the right or 1 millimeter to the left, which may lead to structural problems in the airframe, which would be potentially disastrous, right? And that kind of accuracy, or it could also check if the rivet hole is circular enough, not like an ellipse. If the guy working with the punch or the tool, if something was wrong, it may distort the hole that was used, and that for the rivet, and that kind of thing no human would be able to do. So the in that scenario, actually using edge detection and subpixel accuracy measurements, that system performed very well, better than what humans could. But that's a very specific kind of application. And the big trick in computer vision is often that as long as you can control the lighting, then you're golden. You can set it up, you can control the environment, then you can do some amazing things with your vision system. If you do not have control of the lighting, then it becomes a lot more difficult. So, let me think, maybe I'll implement that and then we can... Then I can tell the story. So I'll do the implementation first, then I'll tell the story behind it. So here, for this particular image, what do you think? Where are the edges?
The outlines of the temple.
Yeah, those would be, clearly most people would mark those as the outlines of the temple. And okay, now why would you say that's an edge?
It's like the perimeter.
Yeah, but in a sense, we also have perimeters here, right? We have the individual leaves here. That would also be a perimeter, right?
Yeah.
Maybe changes in color.
Yeah, we also have changes of color here.
So maybe also the leaves have the
Yeah, so the point is, it really depends, and this is one of the key lessons of any computer vision algorithm. It really depends on your application. What an edge is very much depends on what you're trying to do. Like most people looking at that picture, right? They think if we're looking for edges, then maybe we want to cut out these pagodas, right? or maybe I want to highlight them, brighten them, darken them, do some kind of processing on them, right? But if you are a botanist and you're trying to estimate the health of the lake, for example, then for you maybe it would be much more important to try and segment out the size of the leaves so that you get an estimate of the average size of the leaves, or whatever you have, right? So the one important thing to keep in mind is that whenever you're dealing with a computer vision algorithm, you're really not dealing with that algorithm by itself. You're dealing with it in context, and it always depends on two things: the application, what you're trying to do. So you must be very aware of this, right? And as a word of caution, just using YOLO doesn't mean that YOLO knows anything about your application. So usually you can do quite a lot better by thinking about the application that you use, seeing which kind of deep learning architecture fits into that particular model, and what you're trying to achieve. And the second thing is the data. What kind of data do you have available? What kind of cameras do you use in order to take the images? Are they webcams, mobile phone cameras, which give you slightly better images? DLSR cameras, or is it some other kind of sensor, infrared cameras, for example, which give you very good brightness value, but very low spatial resolution, for example. So when we're discussing algorithms like edge detection, it really doesn't make sense to talk about edge detection without a particular context that what you're trying to achieve. That's why there's no such thing as the best edge detection algorithm either, right? Because for any kind of detector, which is true not just for computer vision, but anything in machine learning, when you're trying to classify things into group A or group B, or group A, group B, group C. There it's also critical to think about the types of errors that you may get, and we'll look into that a little bit later on. So I shared the notebook on the Discord channel, so you can open it, and let's go through edge detection. Yeah. Okay, I have to. So let me just update the link. And just here for this particular notebook, when I said that controlling the brightness is very important, I wasn't joking. Here we have an example of a picture. Right. And using that picture, what color is square B?
And dark gray.
Dark gray. And square A?
Darker gray.
Darker gray. So black or white, maybe?
Ah, okay, yeah.
Closer to white, closer to black, right?
Yeah.
Okay? Wrong. They're actually exactly the same brightness value. It's a trick question, it's an optical illusion. Square A and B have the same brightness. Now, if you tell that to people, they tell you that you're crazy. No way, right? Nobody can see those two as exactly the same brightness. But I can write a simple piece of Python, NumPy, that if you haven't used before, it's actually quite powerful. You can have NumPy arrays, you can ask it for various conditions. So I can say where that image has this color value, 120, then replace it with 255. So I color it in as red, right? So if I color in the squares that are 120, then you'll see both of them are colored in except the A letter there. So they are actually, at the pixel level, they're exactly the same color. So now, the question is, why does that happen? Why does your brain think that those two pixels, that those two squares are different brightness? And then people come up with different hypotheses, right? So some of them say that actually the reason why that happens is because this is a computer generated image, but this particular cylinder here clearly sort of infers a three-dimensional scene where we have a cylinder there, not just a green blob of pixels. And also, the shading on this cylinder tells us that the light is to the right, right? The light is coming somewhere from here. And then this will be the shadow of this particular cylinder. And your eyes actually say those two are the same brightness, but your brain overrides that because it says, no, impossible, because one of them is in the shadow, so it must be a lot brighter to still have that brightness value. And the other one is in the bright sunlight, so it must be a lot darker. And that's one interpretation for why this happens. But we can actually test that. Because if I blank out the cylinder and the other part of the field, then actually the effect is still there.
Yeah.
But not quite so strong, right? B is still light, A is still dark.
Yeah.
So how can we convince our brain that this is actually the same color? What else can I change on the image? Or how can I change the image so that our brain will think that this is so that you actually see it as the same color?
Remove the shadow.
Okay? I could do that, but then how do you want me to do that, Bryce? Then of course it's going to be, I cannot remove the shadow without changing the pixel values, right? If you say remove the shadow, what you want me to do is increase the brightness, which then, of course, the two would be different. So one trick that I found that gets rid of the effect is if you actually connect them,
Oh, yeah, oh.
right? So if I connect the two, now they are the same color.
Got it, yeah. Wow.
Right? So I just paint in the 120 square there in the center, and now it's the same color for people. So this is quite an interesting effect, I think, and it tells you a lot about the human visual system, that indeed it's very sensitive to brightness changes and very sensitive to three-dimensional inferred information due to light and shadows. We're very good at interpreting light and shadows. Computer vision systems nowadays, there's been quite a bit of work on that, of course, because it's very important. But in general, they are much poorer performing than the human brain is. So that was a small interlude. So let's get back to edge detection. So I downloaded a picture from a movie, a very famous one. And anybody know the movie? No? Casablanca.
Oh, Casablanca.
Yeah. So it's a very famous movie. Now, when we're dealing with edge detection and lots of other operations, the basic engine that drives that is convolution, which simply means that we apply a weight matrix to a pixel, and we multiply the neighboring pixels with that particular weight matrix, then add them up and then sum them up. That would be the value that we use for that particular pixel. So when we represent it, we only give the value of the weight matrix, and then that corresponds to the neighbors that we include in our processing. Since we have to replace the one pixel, the convolution matrices are usually odd, because in that case you have one defined center pixel. Right? If you have a 4x4 matrix, if I have a 3 by 3 matrix, it's easy, right? Which one is the center pixel? This one here. That's what I'm trying to override. If it's 4 by 4, then that pixel will be here, so it's not quite clear which one you actually want to change. So there's probably some particular application or domain where even space or even numbered convolution matrices make sense, but in general they're always odd. I've never seen an even one, but I don't think, I mean, there may be some application. One other problem that we have with these convolution matrices is we have to decide what to do at the border, because here I'm processing this pixel and I'm looking at my top left neighbor, or my top neighbor, top right neighbor. But of course, if I'm at the edge of the image, then that may not exist, right? The top left neighbor doesn't exist if this is pixel 0, 0. So then the common methods that are employed in this case are either you extend the image, or the simplest one is to pad the image, which means you add rows or borders of 0, 0 around it, right? Or 128 or something like that. You can extend the image, which means you take the last pixel in the row and then copy it 2 more times, or the last pixel in the column and then copy it n times in order to sort of copy the value of the last pixel. And in some applications it makes sense to wrap around. For example, if you have LiDAR scans or something like that. So now let's have a look and see what happens when we apply various convolution matrices. But let me change this code. Now, I wanted to fix that a while ago. Here, there's a library called SciPy, which has very efficient implementation of the convolution operation, right? They even call it Convolve 2D, and it's written in C++. It's very efficient. It runs much faster than if you're trying to write your own Python code to do that. So I've been using that for quite a while, but the problem with it is that this SciPy library was developed by signal theory people, not computer vision people. And the signal theory people actually do exactly the same thing, right? Except they don't call it convolution, they call it correlation. And the sign is inverted. So the interpretation of that convolution mask is different. So that makes it confusing for computer vision people. So that's why let's implement our own convolution operation using NumPy arrays. And it actually took me a while to figure out what that this actually doesn't give us the result that we expect. So I want to define a function, convolution, the way that we're used to from our computer vision interpretation. and what arguments should I have? Like, you should try that yourself now in your own Python environment. But I'll need an image, right? And I need what's called the kernel, which is this weight matrix. And that's all I need, I think. Anything else? No. Actually, I may include the padding, which would probably be best like an enum saying whether I want to do extend, padding, or wraparound. But in this case, we'll just always pad it. Now I assume the image is a NumPy array. So that means it's a two-dimensional array. And that means I want to get the shape, the first two elements of the shape. The third one may be if it's a color image, right? Then that color image would have would be a three-dimensional array, where the last one would be red, green, and blue components. Edge detection usually is only applied to grayscale images, so most of the time it's applied to grayscale images. So we'll see how to deal with this later. So then I need to have an array, and I want to do zero padding. And I also assume that this is a two-dimensional array. Okay, then 3, if it's 3, I need to do pad. Then I want to generate a new array, or I generate a new array of all zeros because I pad with zeros. And then the size of it should be height plus k height minus 1, and width plus if it's 4, then I would need to pad by 4, right? So mathematically, these expressions look weird. Mathematicians probably would replace this with a math.floor instead of using integer division. But then I would have to cast it to an int afterwards, so I stick with generating integers there. Okay, and then we need to put in that image, so an n image, and then that would be from k height divided by 2 to k height divided by 2 plus the height of the image. Let's see if that works. I just want to paste in the image there. So I have an image. Ooh, that's rather big. Okay, so I'll resize it first because this size, 1191 pixels by 1600, wouldn't be a problem for a modern CPU to process. But if you look at it, my lecture slides are all embedded HTML, which means this image must be encoded as a base 64 encoded string, and Google Collaboratory doesn't allow me to use so much memory. So I'll scale it down. And then let's see if we can actually call it something. So I was thinking I could do this with both n-dimensional arrays and like color pixels, color images, and black and white images, but that's actually not so easy. So I can print out the new shape, which is 2 rows more and 2 columns more. So that's correct, right? And then I can also output a small sub-array from some area, let's say 20 to 22, 20 to 24, and 40 to 43. Now, since I did the padding, I would have to change the coordinates here by adding 1. Integers or slices. Not shape, of course, the image. And the two match, right? So at least the copying now, I know that it actually worked. Okay, so how do we apply the weight matrix? There we have to, I mean, you don't have to. How would you implement applying the weight matrix? To a particular pixel.
Matrix multiplication.
Yeah, so we multiply it, right? But if you want to apply something for every pixel, then what does your code look like usually? Any kind of image processing. We have a for loop, right? But we don't just have one, we have two. And what do they look like? How would you code them up?
Rows and columns.
Correct. right? This is what we have in lots and lots of computer vision image processing routines, right? We apply something for every pixel, so we iterate through the image. And then I generate an output image. Right? And every value in there is and there we can use some easy NumPy magic. So here that will be y minus the divided by 2 and y plus by 2. Now the last index is not included, so I need to add a 1 there. So that gives me the range that I have. And then I multiply this by the kernel. Now, two-dimensional arrays in NumPy are a little bit tricky because sometimes we interpret them as matrices. Multiplying NumPy arrays is a little bit tricky because sometimes we interpret them as matrices, and that means when I then have two matrices, A is 1, 2, 3, 4, 5, 6, 7, 8, 9, and I have another matrix B, 10, 11, 12, 13, 14, 15, 16, 17, 18, right? Then if I calculate A times B, what do I actually get? This one, right? Which is, you may think that you would get 1 times 10 plus 2 times 13 plus 3 times 16, right? That's not what happens. In fact, you get the piecewise multiplication. So you get 1 times 10, 2 times 11, 3 times 12, 4 times 13, 5 times 14, 6 times 15, 7 times 16, 8 times 17, 9 times 18. So you actually get what we want in this case, right? That, for the convolution, that's really what we need to calculate. So that's what we want, then I sum it up, then I have the value that I want to add into my pixel. But, so if in NumPy arrays, if you define these as NumPy arrays and you calculate A times B, this is what you get, the piecewise multiplication. If I want the matrix product, then what do I have to do?
Call function.
Yeah, which function? Dot. I need to calculate the dot product. So A dot B is the matrix multiplication. So 1 times 10 plus 2 times 13 plus 3 times 16 and so on and so forth. Right? So make sure that you know which one you want to use, and also when you define these as np.matrix, then it's different. If you define these as normal NP arrays, then you get the piecewise multiplication. If you define them as np.matrix, then A times B gives you this, the matrix product. Right? Now, I usually don't use the NumPy matrices at all because I find it confusing to then, because Python, remember, is not typed, right? So you don't get, all I get is something A and B in my argument list, so I don't really know whether the user is going to send me a matrix or a NumPy array. And if I don't know and I just call A times B, I get two different results. And the other problem is that NumPy array has many, many functions that are very powerful. np.matrix has much fewer functions because it's only meant to be used for matrices. But when you're dealing with images, all kinds of things can become useful. So my philosophy is to just use everything as an NumPy array, and then if I need to use the matrix multiplication, I make that explicit in my code, and then I know that this definitely must be multiplied. And if you have two NumPy matrices and you call np dot on them, then they will also do the right thing. So your code is much more robust with respect to problems in the arguments that are being passed. And I guess if you're interested, this is a library that I made some patches to. It's for writing a bot in the matrix Fediverse setup. But it's really kind of interesting. I don't know any of these people, but if you look at their Python code, then it looks like this. And what's weird about that code, or what's unusual? If you compare it to my program or lots of other Python code,
There's a lot of initialization.
Additional parameters.
Yeah.
what about the parameters? they're not just parameters, as uh, in, in, in standard Python code, there will be command prefix, case insensitive, owner ID, right? Then there may be default value for this particular parameter, so there may be none, or true, or one, or neobot, right? But here, they actually added all the type information, right? What that means is this particular argument is optional, right? And the type of it is async config. And if it doesn't exist, give it a value of none. That's what that line means, right? Here, auto join rooms is a boolean, right? Because it says bool there. And the Python typing library, which is part of the standard Python library, right? It's part of every Python. If you download python.org, just the Python language, you get typing. It's actually quite powerful if you look at it, like here I can specify that arguments are optional, and I can tell it that here I either expect a command or something that I can call, a function that I can call, which takes as argument a context which can be of type anything, right? So I can specify that the keys here must be a tuple which consists of something that is like a path and a string. So two things put in brackets. Combined. So it's quite interesting because when Python became popular, it was one of the first programming languages after Common Lisp that sort of had implicit typing only, dynamic typing, right? It's a dynamic programming language. The whole point was for dynamic programming, the argument would be, well, why was that seen as better than the C kind of programming where you need to specify, like if I write this function in C,
Of course it doesn't work.
if I write this function in C, then this wouldn't work, right? I couldn't do this. I couldn't just say an image in a kernel. I'd have to say what type it is. Now, passing an image in C is not so easy, because it would be a two-dimensional array, right? So you would have to go like in star star. Star star in a pointer to a pointer to an image. But it's not really a pointer, it's an array, right? And then once I do that, I don't know the size of these things, right? Because it's a pointer to a pointer, I don't know what the width and the height of it is. So then I need to pass that as extra arguments, so then you would have height and width. And kernel I could classify as int. Okay, if I have only 3 by 3 kernels, I would be able to go in 3, 3, like the square brackets, right? So Python here doesn't need that. So the argument for dynamic typing was that it is easier, faster to write sort of proof of concept programs. Development would be faster because I don't really care about the types, right? I don't need to worry about exactly how to classify this. And in fact, C typing can be quite tricky to get right. Probably none of you used that, but there used to be a Unix program called cdecal for C declaration, which would allow you can type in I want to have a pointer to a function that takes an int and an array of 2 integers, and it would generate ampersand, and then in bracket f, and then what the argument would be, because this was quite tricky to get right. So the argument for Python was that, or dynamic programming languages in general, R is the same in that sense, right? Was that you could faster write code because you don't need to worry about the types. But now they've sort of come full circle, right? Because if you look at the NeoBot code, there's no difference between that and the C declaration of a function. Right? It's more powerful. The type system, you can have union types and additional types and subtraction types and all kinds of other things. But in general, basically, you type the whole thing. At least, if you look at this, and I was talking to a student of mine, Jas, who is he's now working for Dropbox. He was at Google before, and now he's at Dropbox. And when he was at Google, what's his name? The Python guy. Guido von Rossum, yes, he was also at Google. And Jas was talking to him, he said, oh, Python, the world, but he didn't know who he was, but he said he told the creator of Python, saying that he thought the world would be a much better place if there was no Python, if they never invented Python. So that's a pretty big stretch, but Jas is a clever guy, and he did have some arguments. Now, I don't agree with it. I like to code in Python. I think it has very nice syntax. It's very easy to read code. Like even if you don't know anything about the typing library, this sort of makes sense. Compared to C++, which if you look at template-based programming, is a nightmare. And lambda expressions, like once you have that in your code, it's really hard to parse to see what the hell this actually is. Is this a definition of a function with a type behind, or am I actually calling something here, right? And the whole meta-programming using templates is crazy. So the Python syntax I like a lot, and I think Python clearly has established itself. Like it does something right. It's the most popular programming language in the world right now. So, but I would really say that if you write Python code like this, right, then you might as well just use TypeScript, because that's a typed version of JavaScript that is standardized by Microsoft that does all of this and a lot of other stuff better. So if you want to use typing, then use a language that requires you to do static typing. You also have better tool support, and it's actually checked at runtime. The problem with the typing here is that this doesn't actually, this is only checked during execution time, so you don't get any errors. Now, I know exactly why Jas, by the way, why he was not a fan of Python. That was because of the dynamic typing nature. He had developed some code for Gmail, and Gmail, of course, that's if you are like a software developer at Google, they don't just let you do GitHub push to Gmail, right? Because there's like millions of people every day that depend on it. So if you get to contribute any code to Gmail, right, it's like a small part, and it's tested on a couple of servers first internally to see if anybody has problems. and then it's shipped out to a couple of servers with actual customers, but a small group only, and then if that runs for several weeks without any trouble, then it gets shipped onto the whole Google Gmail code base, right? Because this is not like me as a professor writing some code, and then if it doesn't work, I reset my robot, we try again, right? So he wrote some code for Gmail, and everything was running fine, and everybody was happy, and they kept increasing it. So then something went wrong, and I think he basically, Southern California didn't have Gmail access for like 6 hours because of him. They called him up in the middle of the night. This is a huge thing, right?
Yeah, of course.
So what happened is, it was a problem with the dynamic typing, and he had a function that took some arguments, and he was executing the code. And for those kind of things, if you need to worry about the code breaking or not, then of course the first thing that you need to realize is that the standard code path is never the problem, because the developer already tested that, right? Just to make sure that the functionality is there. So the standard code path is never a problem. The problem is always what's the other part of the code that you have? The error code path, if something goes wrong, right? So, because that one, usually when you do your development, you're always in the functional part most of the time. Developers are terrible. My students, horrible at testing for whether, like every C function that you have in the Unix kernel returns an error code if something goes wrong. The number of my students that actually test that error code to see whether opening the file actually succeeded or not is very small, which can lead to big problems, because you simply start writing to a file that doesn't exist, but students don't check, or it may have existed at some time in the past, but now it's been deleted. You keep writing to the same file, then f.write, which is the function call for writing, or write fd in C, will simply give you an error, but nobody checks that. They just assume that the write succeeded, right? So we had problems at the robot competition in Italy one time, in Padua. 3 o'clock in the morning, we couldn't figure out why our server was not running. But the problem was this: we had a program that would generate the configuration file, but that configuration file already existed and had the wrong permissions for some reason. So when the system tried to open it, the open would succeed, but it wouldn't be allowed to write to it. So we were writing these new configuration values with our other application. Then that program should actually pick our video server, our vision system should pick up the new configuration values, but it didn't. It would keep reading the old values, and we couldn't figure out why nothing was changing after a while. First of all, we didn't know why it didn't detect anything. Then we detected that the values were wrong. Then we ran our configuration tool, and we thought everything was working, and it was simply not checking the return value. So, because it's very tedious, people don't like to do that. And also, a little bit, specifically a problem in C, because in C you don't actually have exceptions. Nowadays in Python, that wouldn't happen anymore, because your write call could trigger an exception, which then would at least tell you that there's something wrong. So Jazz's problem was that in the error code, if one of the servers, the network ping delay was too high, then Gmail switched to doing something else. But that never happened in Southern California because they have very good network connectivity. And in that part where he needed to switch to a different kind of processing, he just wanted to print a message. But instead of having the log entry as a string, he got it as an array, which then meant that that element only had an index 0 but no index 1. So when he was trying to add in his log information, it would crash. And the only reason was that California had some kind of heat wave, so Google had to shut down. Google shut down some of their data centers, which is why the ping delay on the Google Mail was higher than it ever was before. And that kind of thing in a static language in C, C++, that would have been completely impossible. That would have never happened because nobody, no program would be able to send you a list of messages as opposed to a message, a single message, right? You cannot have char star star and send a char star. Then the compiler will already complain. Python will just accept that. And that's why that was his story with Google Mail. Gmail, not Google, yeah, Gmail. And you can see how this is particularly a problem for library developers, people that develop programs that other people are calling, right? So this neobot thing here is like a library, like NumPy array or something. And they want to make sure they only get the stuff that they actually expect. But if you, so for libraries, I think it makes a lot more sense to code stuff like that in TypeScript or any of the other statically typed languages. Then you don't have that particular problem. You don't need to worry about somebody sending you the wrong thing. So I was very surprised, but they are good developers. I mean, their code works, and they use the latest features of Python. I don't know if I have an example of the .colon here. Not in this code base. That's just one of the new features where you can test and define a variable in the outer scope in Python, which is rather recent. So I think that's like Python 3.10 or something. Anyway, let's get back to our thing here. So I can do the piecewise multiplication. And then all I want to do is add them up. No length, of course. Just height. I already took that.
0, 0. So 3, 3 is correct. So, cool. So now we need to debug this. So let's see what that actually is. Let's have a look at the shape of that. 0, 0. How come this is 0, 0? Y minus k height divided by 2. Three, 3, 0, 0. And of course, if you run that locally on your laptop, then it's easier to use PDB, the Python debugger, instead of having to put in all these print statements, but that doesn't work so easily in the Google Collaboratory. There is a, you can check the variables, but I don't think you can actually check it. In here, like I cannot set a breakpoint as far as I tried it last time. So let's just print them out. Y plus, y minus. Plus 1. Ah, yes. So that's the problem. Here, my new image, when I access it, when I access Y0, I actually need to add 1 to it. Because the image is shifted now, right? So that's correct now. Now I get the 3,3 correctly. And now stop. And now the values have changed. Um, oops. And for the image, when I return this, actually, I don't need to pad the output image. So this should just be height and width. But now it multiplies something, but the problem is, first of all, let's check what that size is. Actually, most of the time you have problems with a NumPy piece of code. The first thing to do is to check the sizes of the things that you're actually dealing with. And now it's correct. The new image that we pass in, and I can do a sub image of that and the output shape that I get. Now when I pass in the particular kernel here with 0, 0, 0, 0, 1, 0, 0, 0, 0, if I draw it on the board, it'll look like this. Simply a 1 here, which means that that's like the identity matrix. It won't make any modification to the image. Now I can change it to 0.5 here, for example. And then I get half 52 divided by 2, 18 divided by 9, 3.5 instead of 7. Now, since I use floating point numbers here, since I use division here, I get floating point numbers as the output, not bytes. The input is an array of bytes, the output will be an array of floating point numbers. which is actually quite useful in lots of further processing. So I leave it like that. I don't convert it to integers. If you wanted to, you could add like as int here at the end. Or as data type to define it as uint 1 byte and things like that. So now we have our own convolution function, and it does exactly the way that we expect it to work. So let me replace this line here. Yeah, and I could have added the mode part to it, same, 0, or wraparound. And I don't want to use the SciPy library. So then let's have a look at this particular convolution mask. What will that actually do? If this is the kernel that I apply, well, that simply means that here I have a 5x5 kernel. Right? So this is my center pixel. And the center pixel is calculated as the sum of multiplying this weight matrix on top of the original image. Which means my top left neighbor I don't care, top all of these I don't care. The only number I care about is my right neighbor. Right? And I take 1 times my right neighbor and replace the center pixel with 1 times the right neighbor, which will shift the image to the left, right? And this should actually happen. And here we can show it in we can show it here with our convolution mask. If I take the numbers from 1 to 25, reshape them as a 5x5 image, and then put it into the image, and then call convolution on it. With this particular mask, that will shift the pixels up, right? So that's what we get here because we're setting it to 1. And oh, no, where's the error? Image 2 is not defined. Ah, image 2. Now it actually shifts them up. So that's the 25 by 5 blocks that I was dealing with, right? Now it's at pixel 0, row 0. And then now for the convolution matrix, if I actually do apply so here that can be image 2 is the convolution of image from 1 to 6, so let's go 0 to 7. Then that will be the convolution. Here is the convolution if I call the SciPy function. And I'll just show the difference between those two. Because that can get confusing, admittedly. Oh, kernel. Convolution. So then you can look at the difference. Here's our input image, right? This is the kernel. So in computer vision, we expect this to shift the image to the image moves, the pixel from there moves to there. So that would be like shifting the image to the left. Right? Here. So this is our standard convolution, the way that we understand it in computer's vision. And that image compared to the original one is this part is shifted to the left. Right? Left 1 column. But if I apply the convolution from SciPy, then the image is shifted to the right, if you look at it, right? And the reason for that is because the signal people have a different interpretation of that convolution mask. In computer vision, we expect it to, but they are reciprocal, inverse in a sense. In computer vision, we look at this as a weight matrix. So I say that center pixel is calculated and it gets weight from this one. So this moves to there, right? The signal people, when you deal with correlation, it's actually exactly the same thing, except you're talking about
the center pixel contributing weight, so some value here, and that value is distributed over the signal. So how much from this pixel gets moved into that pixel? 1 times this value. So it's exactly going in the inverse direction, but you end up with different convolution matrices. Not the output is different. However, most of them you can use in order to do edge detection and things like that. And of course, the convolve function would be a lot faster. Actually, let's check that quickly. So, because that's actually one of my favorite Python modules. The timeit modules are not a favorite, but it's a very useful one. So we can pass in, let's calculate the convolution over the image. So we run test 1 with an image and let's call it 20 times. That'll be too small, 50 times. And let's take a 7x7 kernel. So 7 times 7, 49. And reshape it into 7x7 array. Right. And then we return the image. So now I just apply the same kernel 50 times with an image. So let's run test 1, image. Okay. I left some print statements in there. No print statement. Whoa. 10 to the 139. Holy cow. That's... Well, where is... Okay. So now we can test it. Let's not return a value. So I can time it
and I set the loops to I think that's what it's called. Number. So by default, it calls the function 1,000,000 times, which is rather excessive. So I don't want to wait that long, but we can call it 1,000 times. So now it calls test1 1,000 times. It discards the first couple of calls in order to wait, not a callable. We have to put that as a string, I think. How come it's not defined? Ah. I think we need to pass in. So here about 20 seconds. Now let's try this with the (2D), convolve 2D. Oh, it's slower. Okay, that's surprising. Is it because image is different?
So Professor, if I'm correct, the convolution that we are trying to implement now will be a step in edge detection.
Correct, yes.
Ah, okay.
Yeah, and in fact, lots of other computer vision algorithms are based on convolution.
Ah, all right.
So it's important to, we'll go in a little bit, we'll go through some of the other applications of convolutions. You can adjust the brightness, you can blur images, you can sharpen images,
Okay.
you can find patterns in an image.
So I guess there is some mathematical background to this because it's strange. Like you have a matrix, you multiply the pixels, and you have all these effects. Like,
Right.
how does that?
The the underlying mathematics is just this, the convolution, right?
Ah, okay.
While this shouldn't be running so long.
Maybe
I expected this to be a lot faster.
the number is 1,000.
Yeah, I just changed the other one to 100. It was 1,000 when I ran the first test. That's one of the problems with, the only thing I can think of is that that image was already a floating point image, because here it comes in as a integer,
Oh,
Okay.
but here I tested on a floating point number, because the output of this would be floating point. And then I called it here, so I'll interrupt this. I set it to 100 and I define the image first. So we just take a set of ones of size 500 by 500 and np dot d type is equal to np dot uint 8. And oops, where are we? So let's run that. Okay, now it's getting weird. I think Google slowed me down now after running the processor. So here we just have introduced a particular operation, convolution. Now let's have a look and see how we can actually use it while we're running the timing thing there. That's my right. It's not too high. So how is convolution useful in detecting edges? Now, if this is along a row, right, and this is our brightness, and this is our column, x, then I think most of us would agree that here we have an edge, right? Because I have black, 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 white, 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 black, 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 so on and so forth, right? These are the individual pixels. Let's say like that. And of course, we would also have an edge here, but it would be going in the other direction.
right? Here we're going from black to white, here we're going from white to black. And let's say the brightness here in the most extreme, this is 255, the other one is 0. So in that case, it will be trivial to find the edges. But of course, in an image, it's not so, in a natural scene image, it's not so clear cut, not so easy to do that detection. So if I want to look for an image, then what kind of algorithm would you use? Because in a real image, maybe it looks like this. Right? There's some noise to it, and it's not going to range to move from 0 to 255, or 0 to 1, but it will be some values in between, right? So in that case, how would I detect an edge? Like here, with those 2 pixels, right? Then most people would agree that at this point we have an edge. But what makes that an edge? Or if my image looks like that, then is there an edge or not? No, right? Most people will claim that this is not an edge. So what's the difference between here and here, for example?
Derivative is high.
First of all, yes, the derivative is high. Why the derivative? What do we mean by the derivative? And most people won't, unless you're mathematically inclined, most people won't start by thinking about the derivative, even though mathematically that's the correct concept. But the simplest explanation for why there's an edge is because this value is very different from this value, right? If the image is like this, then clearly there's no edge, right? So it's really the difference between x minus 1 and x, right? If that value is roughly the same, then we don't think there's an edge. If there's a big difference between those two, then we think there's an edge. So that means we're looking for how much the value changes, right? But if I want to determine how much the value changes, then if we look at calculus, and the early computer vision researchers were actually all mathematicians, right? They were the early programmers in the 50s, 60s. They came all from the math department. So for them, the language that they used to describe their work was mathematics, which I think is actually a problem nowadays, or a problem in computer vision literature in general. It's very math heavy, even though the mathematics does not really help in the understanding of the algorithm. So I try to represent things not with the mathematical slang, right? And the problem is that, for example, if later on we'll talk about optical flow. When you talk about optical flow, then the mathematicians, the computer vision papers, they only tell you this: the gradient of the image function, right? And then they use that. So what's the gradient of the image function? The gradient is defined mathematically, so it's a partial derivative. It's like, for a single variable, if you have some function, x is equal to, y is equal to y is equal to sine x, for example, right? Then you can calculate the derivative. This will be f of x. Then you can calculate f dash of x, which is the first derivative, which would be, is it cosine? Are you sure? I'm not sure.
coming from us.
Is it? Yeah.
He's the one.
I'll trust you on the cosine then, right? So that tells you that the derivative, first derivative of sine is cosine, and the first derivative of cosine is
Negative sign.
okay. Good. I'm just checking you because I knew that. Now, if you have a variable, when we're dealing with images, right? We don't just have one variable, we have two variables, usually row and column, right? So this is called a multivariate function. In this case, the derivative doesn't just exist, but there's two components to it. There's sort of the direction in x and the direction in y, or whatever your arguments are here. So that means we can calculate the partial derivative with respect to x and the partial derivative with respect to y, right? Or possibly any other arguments that we have, right? And if you calculate that for every component of your every argument, then that's called the gradient, and they use this symbol, right? Now, for mathematicians, this makes perfect sense, and in their papers, they use the gradient I. You see this in tons of computer vision papers, but actually it is problematic because we're not dealing with sine and cosine, right? We're dealing with images, which is the response of the sensor. So there's no such thing. It doesn't help us to specify that this is the gradient because we cannot actually calculate the analytical solution for this. If I end up afterwards with like x squared plus y multiplied by the tangent of y, then that makes sense, right? Then I can shortcut a lot of the computation. But since we have an image, since we have something that the camera looks at, the only thing I can do is numerically estimate what that gradient would be. And the problem is that a lot of the estimation here, if you want to calculate the gradient, what you have to do is calculate the response of the convolution, the edge detector, in the x and the y direction. But there are 50 different methods easily for calculating this gradient. And which one you choose can have a very big impact on whether your further processing actually works or not. So just putting there gradient I basically means that you're just telling the guy to use any kind of edge detection, and you hope that it gives you the right result. So my view is that in the modern day, the computer languages are a better way to express this. Here, a lot of detail is hidden behind this description, behind this language of mathematics. But it's not good to hide that because that's crucially important for getting your program to actually detect the rivet holes correctly so that the Boeing planes don't fall out of the sky. But a lot of the older professors, they swear by this, right? Even though I don't think replacing convolution or saying apply the Sobel edge detector and then do the following processing doesn't make this any less scientific or more scientific, right? This is just a shortcut for the language that they're used to, but it doesn't gain you any additional insight because it's not like by looking at it as a mathematical gradient, we could actually calculate the analytical solution to it. all we can do is do a numerical approximation, but it scares students away. It's a very concise representation, which, because it's concise, it looks very cool, I guess, but you hide a lot of details that is actually important for developing the full working system. So let's have a look at, wow, this is really going now, 13 minutes. Did I make the image larger or something? Yeah, I think Google shut me out. But, okay, now we want to look for the changes from the left pixel to the right pixel, right? If there's a big change, there's an edge. If there's no change, then there's definitely not an edge. So, okay, mathematically, yes, that will correspond to the derivative. Now, how can I look for the changes between my left neighbor and my right neighbor using a convolution mask? And I want to use a 3x3 mask. How can I use a convolution mask in order to calculate the difference between the current pixel, the pixel under investigation, and the left neighbor?
Shift the matrix and then subtract the original by the.
Yeah, except I could do that, and in this particular case, that would work, and it may be faster, but it wouldn't really be a convolution, because convolution still be applied pixel by pixel values, right? So if I want to represent it as a mask, then I can use the same idea though. If I want to know the difference between myself, this is myself, right, the pixel, this is my left neighbor. I want to calculate the pixel xy minus pixel x minus 1y. Then this convolution mask will exactly do that, right? That's the same thing as calculating. Okay, that works. That will give me a response in the along the row, right, along the columns, which means that here I would get a strong response if along the columns this will happen, right? So what kind of features would I be able to detect using this convolution mask if I then look for values that are large here? So I said this convolution mask, the output of this convolution mask must be greater than some threshold t. Then what do I detect? Yeah, but what kind of edge? If I'm looking at an image, right? And I have this shape, right? And this is white, and the other part is black. Then which pixels are going to have a strong response using this convolution mask? Here?
The outline basically.
The outline, yeah.
Because that's the one that.
But which, so this part?
The olive.
This part? This part?
Yeah.
This part?
And then,
No.
I don't know.
No, this part wouldn't have a strong response using this
Oh,
convolution
this
mask
is
here,
the
right?
lowest.
Because here, we're only comparing the left neighbor to the pixel itself. So here I get a response, but here these pixel values are all going to be the same,
Oh,
right?
so you're focusing on the left.
So we're looking at this part here. Okay, how about this pixel here?
Not much, actually. I'm assuming that the inside is also black.
Yeah, inside is all black. It's not hashed, it's actually all black.
So
I
there's
just,
nothing.
no, actually there will be a response, but the problem is
It's less than the threshold.
it will be a very strong negative response, right? Here, from black to white, my pixel minus the left neighbor will be very large value. Here, it's going to be a very small value negative, right? So this one is also not going to trigger on greater than a threshold. So the first problem that we have when dealing with this is we need to think about the absolute of the values, because transitions from somehow we have to deal with this dichotomy from black to white and white to black. So one thing we can do is we can take the absolute of these values, right? If you want to, you could also generate, you could also shift the output value, like add 128 to it and scale the image somehow so that the output image will be between 0 and 255. Then that makes it somewhat easier. Sometimes we have certain applications where actually white to black and black to white really is the same. Sometimes we only care about white to black transitions or only black to white transitions. Depending on what your application is, that may make a difference. Right? But usually we apply the absolute of this, or we scale the image so that we shift it up. The 0 point we shift up, and then we reduce the scale so that it fits between 0 and 255. Either way will work, but also, more importantly, here we have a problem because here we have an edge, right? But that edge doesn't actually trigger anything in our matrix. So how do we deal with that?
Different convolution.
Yeah, in this case, that's why we usually have different convolution masks. In the case of and basically using this mask, we would trigger on vertical lines, right? This will only give us a response on vertical lines. If I need to know the horizontal lines, I need to have an additional mask here. So these are actually called the Kirsch masks and are very easy, sort of very primitive edge detectors. But you can see how they relate to the derivative. Right? The derivative really only means we want to look for changes in our image function. Now, a couple of extensions to this. If you're dealing with robotics, then you learn very quickly that if you have a sensor, for example, right, and I have an ultrasound sensor in order to detect the distance of my robot to a wall or to an obstacle. If I do that, then if I'm dealing with the actual signal and I measure the distance to the wall, then that's okay. But of course the sensors, the cameras are always lying to us, right? So there's always some noise in the system somewhere that gets added to it. And if you're dealing with the system itself, it's okay. So here would be Y, right? The actual signal that I'm sampling, and I'm doing some processing on it, right? And there's some noise added to it. Now I'm dealing with Y dash, or if we're doing this based on time, then it would be Y dot, right? So that means we calculate the first derivative. In the case of a robot and an ultrasound sensor that measures the distance to the wall, if I look at the derivative of that signal, what does that actually tell me? That would be the change of the distance to the wall, right? Which would be the velocity with which I approach the wall or drive away from the wall. So here, with a normal noise, you're usually okay, right? But if you're dealing with the derivative, if you're now trying, for some reason you have to estimate how fast you approach the wall because you need to brake the robot exactly at the time, for example, with our soccer playing robots, right? We need to, we have a goalkeeper. The early days, now we have humanoid robots, but the early days we used wheeled robots. So if somebody shoots the ball at your goalkeeper, the goalkeeper has to drive and then intercept the ball, which means it has to stop at exactly the right position. In order to be able to do that, we were measuring the distance to the right goalpost and the left goalpost respectively. And then we need to, that tells us what our velocity is. Then we need to stop the ball. Since you're using the derivative, any noise that you have will be greatly amplified. So the velocity estimate is going to be much worse than your position estimate. If you're tracking the ball, right? If you want to estimate the position of the ball from your camera, that's okay. If you need to estimate the velocity of the ball, much harder. So you don't want to use derivatives unless you have to. So if you had a sensor, for example, some kind of, the ball emits a sound wave and you calculate the Doppler effect. If it's fast enough, then you're gold, right? That's your sensor data. That would be a lot better than trying to use the vision system. If, in real applications, if you have a sensor and you can calculate things like the average position of the ball, right? Then this was going to, independently of whether you have noise or not, this is going to be much more robust estimate. Now, in mathematics, if we sum up over the signal, then we get, in the discrete case, the sum, right? But in the continuous case, we would get the integral. So if you can integrate your sensor settings, then that's also great, right? There's lots and lots of different values. Even if one of them is noisy and is a little bit too high, a little bit too low, it doesn't really matter. You get a good sensor value. In fact, if it's true noise, which means it's a normally white noise, it's a normally distributed random process with a mean of 0, then that's going to cancel out. You don't even need to do anything, right? So if you have Gaussian noise, then if you calculate some kind of average, then this is all fine. Nothing is going, you don't need to do anything to deal with the noise. So if you can integrate the reading, then that's great. If you can take the sensor signal itself, that's okay. Hopefully you have a good sensor. If you have to take the derivative, then you may get into trouble very, very quickly. You have to be quite careful. And of course, this is not the end of the story here. We can also start thinking about calculating y dot dot, right? The second derivative. And this one is going to be extremely hard. So if you're trying to measure the acceleration that you have towards the wall, basically no hope to get the reasonable value for that. Which is why balancing humanoid robots is hard, right? Because we need to measure forces, accelerations all the time. And that sucks given the sensors that we have. The sensors are very noisy, and that means you need to filter it. Once you filter them, then of course you have the time delay. Now, the standard edge detection convolution masks, I said this is what the actual derivative would look like. That's usually not what we calculate, because here, spatially, there's some problem with the discretization of the pixels in the image. I cannot know the function value at this position here, for example. Right? I cannot read pixel 2.5 or 2.66 or 2.6057. I can only get the function value at discrete steps. Because of that, we usually take the right neighbor to give us a bigger spread for when to calculate the change, right? And also to not get caught up in the discretization, or to sort of alleviate the problems due to discretization of the image function. And okay, this would be the Roberts edge detection convolution mask, right? And then now I said, if you can integrate it, then you get a much better error response, right? You're much more robust with respect to noise. So we would like to do that. So one thing is I could average over the 3 rows, right? If I'm trying to detect an edge, a vertical edge, and the pixel above me has a big change, and I have a big change, and the pixel below me has a big change, then I'm very sure that this is an edge pixel, right? So that is another way of, another edge detection convolution mask that we can use. And the most famous one, the one that is used in practice all the time, is based on Sobel, which does exactly this, except we replace our center weights for the center row, the one that we're actually interested in, we give it slightly more weight than the other rows. So here, 50% of the response comes from this row, 25% from the top row, 25% from the bottom row. And that is the most famous edge detection convolution mask. And then you can simply take the absolute value or scale it, and then look for where the response is above a threshold or below a threshold. So this would be Sobel edge. This would be the X mask because it goes along the X direction. And then there's Sobel Y, which is the same idea, except now we're going looking for horizontal lines. Now, all the masks that I mentioned, this is all entailed in the gradient sign, right? The mathematicians only write this, and then they ask you to figure out which one to use here. Now, let's see. I don't know why my timing has 1011 seconds. Boy, but 500 by 500. Almost 20 minutes, 16 minutes, yes. So, I don't know why. Actually, I think I want to do it this way. That is slightly better. But now let's go and have a look at so here the convolution masks. Where is F1 defined? F1. Now, why do we have a shift to the left? Shift left, shift right using SciPy. So shift left. But it's really the same thing. It's just two different ways of interpreting the weight matrix, and sometimes it will look a little bit weird if you use one function over the other. Now we can use we can use the convolution mask also to do template matching. In this case, we have slightly larger features, or so here I can take out this particular red square, and this would be my template. I use this as a convolution mask that I apply. In that case, I'll get a stronger response for the patches where this pattern is most prominent. And so we can use that to pick out exact elements out of the image that we're looking for. And this will work. Yeah, so here I just threshold it, which is what you would do for detecting images, also for edges. Then I can have other kinds of convolution masks. This mask here, what will that do? I mean, it'll blur because I called it blur, so most likely it will blur the image, right? But why? that mask, what it says is simply take that pixel and replace it by the sum of all the 5x5 pixels, right? So it takes the average, in a sense, it takes the average of the 5x5 neighborhood and puts that into your pixel, which means that any kind of changes that you have with respect to the other pixels is going to be averaged out. And as I said, averaging is nice, right? Summing up is nice. We get very strong response. So a lot of times, if you have problems with noise in your image and detecting edges, then you can blur the image, and if you still detect an edge, then you can actually be very sure that this particular pixel actually indeed is a edge pixel, right? Because now the average of those neighborhoods is different. And here, that's the blur image. We can also look at the sharpen mask here. This one will actually take a particular pixel, right? And then sort of increase the difference between that pixel and all of its neighbors. Right? So it takes the average difference between the pixel and its 4 neighbors, and then instead of just taking the difference here, we would have a 4, now we make a 5 to bump it up to increase that difference. So that allows us to sharpen edges, right? The contrast will be enhanced in this case. It will sharpen the image. Also, as you can see, I could have a mask here. I sort of just look at the top right, bottom, and left neighbor. But I could also take the top right, the diagonal neighbors as well, and include those in my mask, in which case I wanted to change this to a 9 instead of a 5 there. Because I would have 8 neighbors in this case. So we can run that and look at the output on the Humphrey Bogart image. And here, input image, you can see the blurred image is clearly blurred. And the sharpened image, I sharpened the blurred image, but then the average brightness has changed. That's why the background here is brighter than there. But I get stronger edges compared to this image, right? So this is calculated from this image. I'm trying to undo the blur, which of course is hard because I lost the information at this point. Well, it's harder because I've lost information at this particular point. So we can look at images, and of course, one reason why we're interested in edges is that people can use outlines of things and detect what shape it is, right? Like if I were a good artist, then I could draw something like that, and you would say, yeah, that's a car, right? So we don't need the full color information or anything like that. And a lot of the times when we're dealing with edge detection, it's things like detecting objects, separating them from the background and things like that. And then we would like to group them together to generate these kind of outlines. Right? Usually we're not interested in the particular pixels, but the whole point is to generate some outline around it. So here, this would be our image function along one row, and we would like to detect edges at 100 from black to white and from white to black at 250. And of course that's trivial, but in reality it looks a lot more like that, right? There's all kinds of weird edge pixel configurations that we get in actual images. And this is what you really get from your image function then, right? If I add some noise to the particular image. And then if I ask you the first two images, it's easy to identify what the edges are, right? Potential candidate. Here it's a lot harder. Like, is this an edge here or not? This one here probably, yeah. This one here, okay, we all agree on this, but here these ones are not quite clear whether there should be an edge or not. Which is, I guess, another way of saying that the pixel-based decisions, predicates, are always very noisy when it comes to images. So to detect edges, we don't just want to look at one pixel, but we also want to look at the neighbors to see if they all agree that there should be an edge. Because in natural scenes, if there is an edge pixel at that location, very likely there should be, well, if it's an outline that we're looking for, then there must be another edge pixel above or below or to the right or to the left of it.
Like the image you showed us, the one with the pagodas,
Yeah.
I'm thinking about the leaves.
Yeah.
If we would see something like that, I think we would have a lot of...
Oh yeah, sure. That would be very noisy. Yes.
So that would take a bit of trial and error to get
Yes.
the right edges.
Yeah, and getting the right parameters for your algorithm, which in a sense is one of the things that why deep learning is kind of powerful, because the first level of any image processing system for computer vision that is based on deep learning nowadays, the first level is all what? Not feature extraction, no. The first level in any network architecture for computer vision is usually a convnet, right? What does a conv mean? That's a convolution, right? But instead of us programming the weight matrix, the network learns what the good weight matrix is in order to do the further processing that it's supposed to do. So in a sense, we're not using the Sobel edge detector or the Kirsch edge detector or any other kind of edge detector, but we let the system decide what the correct edge detector should be. Now that's very powerful if your data is covering the whole domain. If it's only a small subpart, you can very easily overfit to the type of images that you're dealing with. So deep learning, yeah, you use also convolution, but you let the system decide what the edges are. So we have an image function, two-parameter function. Edge is defined as a large change. So that's the first derivative. Since it's an image function, we're dealing with the partial derivative and the gradient. So here we have we start with small versions, so the Roberts operator, Prewitt operator, and then extend it to 3 rows. Actually, I think I called that Kirsch instead of Roberts. The Kirsch masks are something different. And here we have the Sobel edge detector, which is by far the most popular. It's been used in tons of applications. Pretty much anytime somebody talks about edge detection, if they don't say anything else, that usually means they're using the Sobel edge detector. And then we have the Kirsch masks. The Kirsch masks are exactly the same as the Sobel edge detector, except instead of just having vertical and horizontal lines, I can also rotate this mask by 45 degrees to get a special response, or have a strong response on 45-degree angles. Right. So the Kirsch masks are actually all 8 of them. Horizontal plus to minus, minus to plus, so the signs are swapped. Or use the absolute, then you only have 4 of them, but then you have the 45 up and the 45 down. So it would look like 0, 0, 0 along the diagonal, 1, minus 1, minus 1, minus 2, 1, 1, 2, and the other way around. So here shows one of them. And here's the output on the Taiwanese temple image, and you can see it has a very strong response on the 45 degrees slanted roof here, like this part there has 45-degree angles, and also still has some response on vertical line, but not as strong. If I apply a standard Sobel edge detector, I'll get a stronger response for the vertical lines there. So here we can apply all of them. And you can see Sobel X. So this has a strong response on vertical lines. Sobel Y, strong response on horizontal lines. 45 degrees up and 45 degrees down. 45 degrees down, I don't think we have so many in that particular dimension. Here we just have a strong response, and that's the roof sloping upwards. Okay, so that's it for today, and I will. So as I mentioned before, we will have joint classes with the German students. They will start next week, Monday. And it will be first, so on the 11th, it will basically be a get-together to meet the German students, and then try and start form groups for the project. And I will post the first assignment also by Wednesday, probably.
What time is the lesson going to be?
We will have regular class at 9, and then the German students, we will meet together with during the motion planning course. It should be at 3 p.m. And then that's remotely, because they're joining from Germany.
Oh, yeah. No. Actually, that's also a meaning for us, because the 4 of us from that university, we're also from the university guys, where we have some seminars, but we should finish in time. So the fact that we connect remotely means we can manage to run.
Yeah, you just need to connect.
Yeah.
And please try and be there, at least for the first meeting on Monday, just so that you can introduce yourself to the German students.
Yeah. I mean, you said next Monday is going to be 9. I think in Europe it's not.
No. It's going to be at 3 p.m.
Alright, great, okay, right.
Yeah, it's going to be at 3 p.m. We will have regular class at 9.
Okay, so it's
And then,
okay, alright.
and then we have another set at 3
Okay.
p.m. But next Monday it won't be an actual lecture, I don't think. It will be more like a get together and talk about the project with Turtlebot.
So they are master students or
They are mixed, same as here, mixed master and undergraduate students, I think. They may all be master students, I'm not 100% sure. I think the course is open to both, but what the actual makeup is, they haven't told me yet.
they are really interesting.
Yeah, so I think it's a nice opportunity to do some joint projects. They also have the Turtlebots, which is a nice, robust robot platform. And we will have to come up with some interesting challenge for the Turtlebot. So we can always play soccer, of course, but maybe do a navigation challenge. The German students are going to use the vision and the LiDAR. So we will, you guys will help them with the vision, and they will be responsible for the LiDAR and the control of the boat.
Oh yeah.